We'll start off by introducing our speaker for tonight for doing the lecture for a vertical empire, history of the British rocketry program. Okay, so just to give a brief biography of Nicholas. So Nicholas spent 35 years teaching physics and is now retired. He's the author of several books, one which is entitled An Atomic Empire, the story of nuclear power in Britain. Another one, Skybolt, which documents the development of inertial navigation and missiles in the UK, and A Vertical Empire, the UK rocketry program from the 1950s and 1960s, which he'll cover in his lecture tonight. He usually spends the summer months cruising the Baltic in his yacht and winter researching government files in the National Archives, a life balance which I think is very agreeable by the sounds of it. Thank you very much, Nicholas. I will hand over to you for tonight's lecture.
Thank you. The book covers the period from the mid-50s until 1971, when it all faltered. We had been involved in rocketry in terms of guided missiles and so on. These were ballistic rockets for missiles, and there's one illustrated here at Woomera. The title actually comes, I was finding it very difficult to find a title for the book, and reading a memorandum where the RAF were wanting to build basically what was a mini space shuttle. The Chief Secretary to the Treasury wrote back and said, I don't think we should start building a vertical empire when we've just got rid of our horizontal empire. And that phrase took my imagination, if you like, and that became the title of the book. How would you go about writing a book like this? Well, as Scott just said, I spend quite some time in the National Archives, at least when they're open, and there are all sorts of files. But what I call the technical files, like this one, which simply takes a vehicle and says, if we did this to it, what would be the outcome? You know, what would be the weights, the payload, and all the rest of it. And what I call the policy files, so that people in, say, the Ministry of Aviation are saying, do we want to do this? And if we are going to do this, have we got the money for it? And what's the best way of going about it? That's what you might call policy. And what I tried to do in the book is merge both policy and technical together, because in isolation, they don't mean very much, but you've got to see one in terms of the other. Other source is brochures put out by the various firms. This is one here is put out by what was called Hawker Siddeley, basically the old de Havilland, and they put out this brochure, which technically was very sensible, but for all sorts of other political reasons was a non-starter. The one on the right actually did go into production. Bristol Siddeley were based actually at a place called Anstey near Coventry, and what they did was basically do build rocket engines and test them there. And this one is the engine for the first stage of the Black Arrow launcher. Now, where did it all begin? Well, we know really, because here's Peenemünde, and in the background is the Baltic Sea, and V2 engineering. Slide, know exactly what it was, because the V2 put all together these technologies, and effectively all modern liquid fuel rockets come from those basic ideas. As a weapon of war, it was ineffective. Two things began to converge. The very early nuclear weapons were very heavy and very cumbersome, but gradually as the technology progressed, they became lighter and lighter, and rockets became bigger and bigger. And so eventually the two merged. Now, the very first ICBM was the Russian R7, or Semyorka, as it's called, which is still being used today as a satellite launcher. It was very large, very cumbersome, again militarily fairly useless, but it scared the Americans. And here we see a modern day launch of an R7. White stuff, it's nice. The external boosters fell away halfway through, leaving the central core to carry on by itself. It was so big that it was able to launch Sputnik, Gagarin, and all the rest of it. And everyone thought Russia had won the space race. Well, in fact, almost the opposite was true. You had to build, or the Russians had to build, such a large rocket simply because their warheads were so heavy, which wasn't true for the Americans. They had begun miniaturizing their warheads, and the Russian equivalent, sorry, the American equivalent, which also burned kerosene and liquid oxygen, was the Atlas. It was smaller and lighter than the Russian equivalent because it carried a smaller payload, because the Americans had miniaturized their warheads, and that put them at a disadvantage in what was called the space race, which is more a journalistic invention than anything else. And here's another rocket, again using liquid oxygen and kerosene, so you will see the ice breaking off as the rocket moves up. There's the ice. So the thrust builds up, and when the thrust is sufficient, the rocket is released a second. Now, that wasn't American, and it wasn't Russian. It was, in fact, British, because at that time, Britain still thought of itself as being one of the big three. So if America and Russia were going to develop ballistic missiles, the UK had to follow suit. One major problem is that there was absolutely no infrastructure. Russia and America had been developing these missiles. They had the infrastructure to launch and test them. The UK did not. It was starting entirely from scratch. And a lot of the technology for the rocket, Blue Streak, was in fact licensed from the Americans. The tank here, that's the liquid oxygen tank, and that's the kerosene tank, were exact replicas of the Atlas. And the rocket motors came from, well, they initially came from a American design, although Rolls-Royce took them over and re-engineered them. To give you an idea how big Blue Streak was, you can see it here on the transporter. It's 10-foot diameter. You can see the welded tanks with stainless steel. Now, to save weight, that stainless steel needed to be as thin as possible. And in fact, if you stood the rocket upright with the warhead on top, it would just simply collapse under its own weight. It had to be kept pressurized all the time so that the pressure of the gas in the tanks would keep it rigid. Here's a cutaway of Blue Streak, the Rolls-Royce rocket motors. These are the exhausts for the turbines. So the not quite the turbine. Yes, the turbine. The turbines would drive the pumps for the rocket motors. And here we have the kerosene tank and then the liquid oxygen tank there. Now, I said the thing was very fragile, and to leave it out in the open, it was hopelessly vulnerable to a preemptive attack. And very early on, the British realised the only way to keep it secure was to house it underground in what was then called an underground launcher, and what today we would call a missile silo. And some of the very early work on missile silos was carried out in the bucolic English countryside in Buckinghamshire. This is a place called Westcott, and it was built as an airfield near the end of the war and not really used. And a lot of these airfields got taken over as government research establishments. And this was the rocket propulsion establishment. Now, at the establishment, they said, OK, fine, we're going to put the thing underground. So we're going to have to fire the rockets. What's going to happen to the half-ton of fuel we're consuming when it goes out up here? Now, Blue Streak was quite big. I mean, they're saying 69 foot for this thing here. The whole launcher would be 130 feet deep, about 40 meters. So you got to dig a hole in the ground 130 feet deep and put this missile in it. And it's not just the missile, it's all the ancillaries as well. They thought, why don't we build a 1/6 scale model, put in a model rocket, with real rocket motors, and try firing them and see what happens. So rather than dig a hole in the ground, they did it horizontally with this brick wall representing the ground plane. For some reason, they decided to choose octagonal tubes here, and there was the rocket. So basically, you would fire the rocket motors, here the propellant supply pipes, and the hot gases would come along there. And of course, it was fairly heavily instrumented to see what would happen. Here's a picture of the model silo. Those of you of a certain age will recognize a quote from the film of My Fair Lady, with a little bit of blooming luck. And so here's our model rocket ready to be fired, and you can see the instruments measure sound levels and so on. And here is where the hot gases are going to come out. I visit. Oh, right. Here is one being fired, and you can see the rocket motors there. Unfortunately, the site has been cleared and no one is quite sure where it actually was. But when I visited in 2010, there were bits of the model silo still lying about. And I think they've been preserved by English heritage. But the model silo you've seen there, basically, this was part of it. And I think it's still there. So they've worked out the design. How about the full-scale thing? Well, full architect's drawings are available in the National Archives. Here's the rocket which comes along. There's a lid on top of the launcher, which weighs 400 tons. You lower the missile here. It sits on a platform. These are hydraulic jacks, because one of the points of this silo is that you might get a 1 megaton ground blast about a mile away. So the whole ground is going to shake. And so basically this thing is supported on these hydraulic jacks to absorb the shock. There's some acoustic lining here. These are access points to the various points on the missile. The crew will come down here and go in. These are the living quarters. That's the kitchen sink, by the way. So yes, they had put quite a bit of work into this, but there are other issues. The whole thing had to be surrounded by a 3/4 inch mild steel liner because of what is nowadays called electromagnetic pulse. Basically, the whole silo was going to be encased in a Faraday cage. It also took up a lot of concrete. All this bit here is concrete, and there's been speculation as to whether the UK construction industry could produce enough concrete to build 60 of these things. Now, it was becoming very unpopular in Whitehall because the time and effort needed to develop the rocket, and then the silos, and that looked like an open-ended check. There were estimates, but they weren't estimates, they were guesses. And from the architect's drawings, someone in English Heritage drew up this model, if you like. There's the kitchen sink, there's the lid, which moved on rails. Here's the entrance there, and of course the missile itself on its hydraulic platform. But where could we put these was another issue, because the thing, as I say, was about 140 feet deep, and the water table in the UK is usually not very far down, and trying to find 60 sites fairly well away from inhabited areas was something of a problem. America had got places like Nevada, Russia had got Siberia, we'd got the home counties, and that wasn't really viable. Now, there was another problem associated with Blue Streak, which was called the reentry problem. Back in 1955, no one knew what would happen if you fired a nuclear warhead at Moscow, because as it came in, it would leave the atmosphere, it would come into the atmosphere again over the target, traveling at about 4 kilometers a second. Now, first of all, everyone knows that meteorites hit the atmosphere and burn up, and they obviously didn't want that to happen. And the second thing is that the deceleration is going to be fairly massive, going from 4 kilometers a second down to perhaps 100 meters a second in a very short time, also gave problems. So the RAe looked at this and came up with a design for a re-entry vehicle, and did some calculations as to temperature, deceleration and so on, height. This was in the days before computers. So basically, these were inspired calculations, shall we say, but that's the best they could do in 1955. Now, it's all very well drawing these, but you've got to find out whether it's going to work or not. And so the RAe turned to a firm called Sanders Rowe, which you are all familiar with, I hope, and said, can you build us a rocket which will launch a miniature re-entry vehicle up into the sky? And Sanders Rowe said, yes, no problem. And they built this, which was called Black Knight. This is BK-03. It actually got a dummy warhead here. It was just to prove that the rocket worked. And this is in Woomera. It was controlled from back here, and the gantry has been rolled away. This is the launch crew standing around. Initially, these were the rocket motors used, burning kerosene and high-test peroxide. High-test peroxide is 80% H2O2 and 15% water. These were replaced by a later version, and these rocket motors came from the small chamber of the blue steel standoff missile. This little knob here is actually the bit that holds it down. If you're doing a static firing, there's some jaws which clamp onto that little ball and stop the rocket leaving the launch pad. The hydrogen peroxide was pumped through a catalyst, which was silver-plated nickel gauze, and it decomposed to steam and oxygen at a temperature between about 500 and 600 Celsius. You could use it as a monopropellant, so to speak, but it's much more efficient to inject kerosene into that mixture, and it was spontaneously ignite, which was quite useful. The ratio was about 8 parts of HTP to 1 part of kerosene. And this is what was called the catalyst pack. So here's a dummy re-entry head. I think this is a BK09. Being prepared, it is going to be hoisted up the gantry and put on top of the rocket. And they picked dark, moonless nights and pointed the camera at the sky where the re-entry was supposed to take place. And it didn't burn up, but it produced a streak of light like this due to the hot air around it. It's often said that the deceleration is due to the friction of the air, and that's not true. It's actually adiabatic compression of air in front of the re-entry head. This streak here will be the rocket body entering at the same time. And then they would go out and look for, in the Australian desert, look for the re-entry head. I can't remember which one this is, but here it is. They drove around in Land Rovers and had a look and eventually found the remains. They instrumented the re-entry heads, as you can see, but it's fairly primitive 1950s electronics with resistors and capacitors and not much more. Here's an odd one. The RAE wanted to know what happened if you had a plain copper sphere. And so they built a plain copper sphere and launched it, and in fact, really not much happened. The Treasury was opposed vehemently to the whole programme and did their best to cancel it. How much did it cost? Well, someone from the ministry wrote and said, how much does it cost? £41,000 for each vehicle. And you got to set it up for testing and all the rest of the launching, and you could add another £7,000 for that. I mean, today those figures look absurd. It actually tells us more about inflation than about Black Knight. Now, Saunders Row set up this test site on the Isle of Wight, just by the Needles, in that sort of natural hollow there. All these buildings are now disappeared, but there are still bits of it left along here. I spoke to the architect who designed all this, and he said one of his biggest problems was pumping up water from Yarmouth, because the buckets here, deflecting buckets, needed a lot of water when you did a test firing. Here it is, the site is just being finished. There were 2 gantries here in which a Black Knight would be set up and test fired. And so the truck would come down and take the rocket vehicle there. But as I said, there's a lot of opposition to Blue Streak, and a special study group was set up. To begin with, Blue Streak carried on because, simply in the words of another Prime Minister, there was no alternative. But April 1960, it was cancelled. This is an excerpt from Hansard. The trouble is that the Minister of Defence gave this statement, and for the next 30 years, it was the only thing historians had to go on. And the vulnerability became a big issue. And lots of historians said it was vulnerable, yada, yada. It was going to be housed in a silo. If silos are so vulnerable, why did America and Russia and China and France build them? Well, in fact, it was an excuse. As I said, up to this point, there had been no alternative, but something came into view. Skybolt, which solved an awful lot of problems for the British deterrent. That opened up another can of worms, which we haven't got time to go into. But Blue Streak, as a military weapon, was abandoned. But Watkinson then said, and really it's a face saver, that the money hasn't been wasted because we can use it as a satellite launcher. And in fact, designs had been going on for some time. Now, back early in 1957, a chap at Farnborough, Desmond King Healy, said, well, if we took Blue Streak and put Black Knight on top at a small third stage, we could launch satellites weighing about a ton into low Earth orbit. Now, this was actually 6 months before Sputnik, so it was actually an interesting idea. Later on, Saunders-Roe was given some money to investigate a further design. This again takes Black Knight, but a larger version with a, instead of 3 foot or 36-inch diameter, it was 54-inch and produced quite a detailed design. And this is their artist's impression of what that would have looked like on the launch pad at Woomera. The trouble was, no one was prepared to pay for it. The defence budget said, no, nothing to do with us. The science budget said, no. And so funding continued at a trickle. But later in the year, the French came along and said, you're building a satellite launcher, would you be interested in a joint venture? And so we said, okay. And so here's Blue Streak. Here's a French second stage, and we kept the British third stage, and we put out a brochure. But we also said it must be more than just an Anglo-French program. We want to be proper Europeans, and we're going to sell this around Europe. And in fact, most of Europe wasn't interested, and it took an awful long time to get the thing off the ground. But an organisation was set up called ELDO, European Launcher Development Organisation. So we have Blue Streak, we have a French second stage, we have a German third stage, we have the satellite and fairings, which were Italian. Now, the trouble with this was that ELDO was set up in such a way that each individual country was responsible for its own part, and there was no one in overall technical command. So trying to integrate all of this was a nightmare. And there were 11 launches and 11 failures. This is what Europa would have looked like. Well, that's what it did look like. This is at Spade Adam in Cumbria, which was the Blue Streak test site, and the French stage, German stage, Italian bit, on top. Here's the fourth launch, dummy upper stages, but Blue Streak. There was one slight mishap at the end of the first launch, but otherwise Blue Streak performed flawlessly, which can't be said of the other stages. Whoops. Now, come launch 11, they're supposed to, the launch site had moved to South America, a place called Kuru, and the 11th launch failed. And this is an excerpt from the report on the failure. Now, who designed the third stage and built it? And the answer was the Germans. And we all think of Germans as being, you know, the engineers of Europe. Well, if you look at this, it's been fairly rude about that third stage. But we'll leave Eldo and Blue Streak for the moment. Return to Black Knight. Now, the RE were very satisfied, very proud of Black Knight. And so they thought, why don't we develop a small satellite launcher using as much of the technology as possible? So it was announced that Britain will now go it alone in space. Here we are, the daily sketch of September 1964. And this was the ultimate design. Black Knight had got 4 rocket chambers. This would have 8. Here's our HTP, kerosene, second stage, HTP again and kerosene, a solid fuel rocket and the payload. There were also 4 small solid fuel rockets there, which were designed to settle the fuel in the tanks after separation. And here we are, here's our 8-chamber rocket motor, and this is an artist's impression. R3 was the last launch of Black Arrow. Here we are, the Gamma 8 as it was called, and the second stage, Gamma 2. Note they've got extended nozzles because they're going to be working in near vacuum and it's more efficient. So here we are on the Isle of Wight again, the needles on the left, and Black Arrow is being set up in one of those gantries for testing. And so it's tethered down, exactly the same as Black Knight with that ball, and the rocket motor's fired. This was effectively the control center, and there were various cameras and so on to record what was happening. There was even at one stage a proposal to launch Black Arrow from the UK, save having to go out to Woomera. And one site was in South Uist, but they reckoned that South Uist was almost as difficult to get to as Woomera. The other place was Brancaster, as we can see here on East Anglia, firing it north. First stage, impact. Now I was reading through the files on this, and yeah, it was very interesting. And then the next was a big envelope, and I pulled out the contents and opened them out, and it was a map of the oil rigs in the North Sea. The chance of it actually hitting an oil rig is remote, but on the other hand, you know, it's a risk which it really isn't worth taking. So that was an idea that died. Not everyone thought that Black Arrow was a good idea. This is an article from the Evening News, and it's not very complimentary, as we can see. The French laugh at it. The rest of Europe ignores it. And eventually it was decided to cancel. Now, to go back to the political side of things, what happens in an event like this is someone at a fairly low level writes a report which is pushed up to the next level and to the minister. Then the minister will push it up, if it's important enough, to the cabinet or the prime minister. And so here we have a meeting with these people present, and the question is, should we go ahead and cancel? And the answer was yes. The Prime Minister being Edward Heath, and he was quite pro-French, as we know, and he was interested in cooperation with the French, but he decided, and the meeting decided, to cancel. That was in July. Now, R3 was almost ready for launch, and so, you know, Saunders Rowe said, well, can we go ahead and finish this? And they were given the go-ahead. And it was to launch a small satellite called Prospero, which didn't contain an awful lot because it's actually very small. One of the drawbacks of Black Arrow is that it was very much a minimalist satellite launcher. And here is Prospero being set up. I think it's built by Mullards. And here it is being set up in Woomera. You can see there's the Gamma 8, and then testing everything. Now the next bit will show how much of a shoestring operation it was. Because here comes the payload shrouds. Carried on this truck in the middle of the Australian desert. So they pick it up, and you can just see Black Arrow inside the gantry there. And some bod at the top heaves on the rope, and up we go. And so, right, they feed it up, they can move it back in, and it's going to be installed. You can see the payload shrouds there. Now, this is the gantry being moved back, and what follows are various shots of the rocket itself on the launch pad. Whoops, oh dear, I've done something naughty there. You see just on the left, we'll see it better in a later bit, there is an umbilical here, and it disconnects at launch, and that thing there is a sort of trampoline, so that the plug is ejected and swings down and bounces off that trampoline. So here we are out in the Australian desert. The people in the control center. And liftoff. Notice there's almost no colour in the flame because of very little kerosene. That's a very good example of shock diamonds as well in that launch. So there we go. That was the last launch. And 1971, that had been cancelled. In 1971, Eldo fell apart. The British had been obstructive for an awful long time. All the launches had failed. Basically, the organisation collapsed, and that was the end of rocketry in the UK. Whoops. So that's the end, and I'll hand back to Scott.
Thank you very much, Nicholas. So we have time for a few questions. So if you have any questions you want to post, you can post them in the Q&A section to the right-hand side. I might as well start off by asking a question of my own to you, Nicholas. Firstly, the collaborations were there any collaborations with the Americans regarding the design and build of silos and reentry? I'm not sure how close these were to the parallel research efforts which were made by the Russians and Americans at a similar time, and I was wondering if there's any crossover of knowledge.
There was certainly crossover knowledge with the silos. In early 1960s, the chap who had basically designed the silos at Westcott, Barry Ricketson, went to the United States and presented his data. And if you look at the design of the American Titan II silo, you can see certain family similarities. That too was octagonal with the acoustic lining and all the rest of it. That fed into it. The reentry experiments showed up a large number of phenomena which were interesting, because if you're going to do missile defense, then you need to know what's going to happen when the reentry vehicle hits the atmosphere. And in fact, the Americans joined in to an extended Black Knight program, which was looking specifically at these sort of effects. We had finalized the design of the reentry body, but we were looking at what happened when it came into the atmosphere.
Mm-hmm. I see. And one further question from myself here. Do you think any research leads were lost by the cancellation of the program, or were we in a position that we'd already lost the lead by that point anyway?
The problem both with Black Arrow and Blue Streak is that effectively they were interesting designs, say in 1960. By 1970, they were just far too small. Yeah. If you look at RAeS, it's much, much bigger. And there were all sorts of proposals to upgrade Blue Streak with strap-on boosters and liquid hydrogen stages and so on. But even then, you were pushing the envelope. Yeah.
It's ironic that where we are now is we want small launches, so we're kind of coming full circle and going back to small launch vehicles again after such a long time. Okay, so just looking at the Q&A sessions, there are no questions coming through. So unless their questions come through imminently, then we will draw close to our lecture. So it only remains for me to say thank you, Nicholas, for presenting your fascinating presentation here tonight. And I might dig out your book and have a read.
Thank you.
Many thanks. Okay, for those attending the lectures for next season, we'll be adding lectures onto our website over the coming weeks and months, so keep posted on that, and we'll also be promoting the lectures as we move forward. Typically the new lecture of the next season will be starting in October with a lecture from Rolls-Royce, so I'm sure next season will be the same as well. So do keep posted on the website for any future lectures that will come through for our next season. So we just have a question which has just popped through. So a question here from Andy for you, Nicholas. We'll just end with this one. How many years were saved by using German technology and engineers after the war? And you're muted, Nicholas.
Unmute. In the UK, not much. We did acquire a few German technicians, but basically that was looking at things like guided weapons. By the time Blue Streak came along, there were very few German engineers, one or two who settled in the UK, but that was all. And in a sense, the HT technology also came from Germany. The Germans were very interested in using HTP in things like submarines and so on. And so we built on that technology, if you like. But the use of HTP and kerosene like that was uniquely British.
Excellent. Okay. Many thank you for your response, and many thank you for your attendance tonight, everyone. And we'll see you at our next lecture, whether that be physically or remotely. Thank you very much.